Welcome to the last video for the lecture Fluid Dynamics. In this video, I would like to discuss the Navier-Stokes equations in more detail. Let's start with the consideration which forces are represented in the Navier-Stokes equations. For this, we look at the individual terms of the Navier-Stokes equations, and we start with the first term. And this term represents the inertial forces. The second term, which is the pressure gradient, represents the pressure forces. And the next term represents the viscous or the friction forces. So this term models the inner friction of a liquid. And the last term are the volume forces. And as we already discussed in the video for the derivation of the Navier-Stokes equations, the volume forces can be quite different depending on the setup of your system. So it could be gravitational forces, centrifugal forces, or electrostatic forces. And it is very important that you know which forces are represented in the Navier-Stokes equations, because if you want to simplify the Navier-Stokes equations, one of the first steps is to look at your problem, think about which forces are relevant or less relevant, and then omit the corresponding terms in the Navier-Stokes equation. And also when we're talking about microfluidics, it is very important to know that in microfluidics, some forces are less relevant than other forces, so you might be able to dramatically simplify the Navier-Stokes equations. The most important thing you should take away from this video is the meaning of the Reynolds number. The Reynolds number is a dimensionless number which relates the inertial and the friction forces. So you divide the inertial forces by the viscous or friction forces, and this is the Reynolds number. So usually if you do this, the Reynolds number for a given problem can be calculated like this, where the L is a characteristic length scale. And in microfluidics, the Reynolds number is usually very low. And what does it mean if we have a very low Reynolds number? This means that the friction is very high in our system. So the viscous forces dominate the inertial forces, and this means that the inertial terms can be neglected. So the left-hand side of the Navier-Stokes equation becomes 0, and this means that we have a linear differential equation. Now let's take a look how the Navier-Stokes equations can be simplified for so-called Stokes flow. This is pretty easy. You can say, okay, we have a Reynolds number smaller than 1, so we can neglect the inertial forces. Then you say we have a steady flow, so we have no time dependencies. So all dependencies all derivations with respect to time are 0. And then in Stokes flow or in microfluidics, you usually assume that you have no volume forces. So the last term can also be neglected. So if we apply all those simplifications, we get Poisson equation for Stokes flow. And the Poisson equation is given here. So you have the pressure gradient, and this equals the viscosity times the Laplacian of your velocity field. And if you look at this Poisson equation, you can immediately see that for Stokes flow, which is also called creeping flow, the driving pressure and the friction are balanced. So you have a driving pressure gradient, and all this energy is consumed by the friction. And for this kind of flow, the Navier-Stokes equations can be solved analytically. So we already talked about the Reynolds number, and we already discussed how the Navier-Stokes equations can be simplified for very low Reynolds numbers, meaning that we have Stokes flow. But let's take a step back and look at a general classification, how we can classify fluid flow with respect to Reynolds numbers. The Reynolds number can be used to identify 3 common flow regimes. And the first one, we just discussed this one, is the creeping flow or the Stokes flow, which is present for very small Reynolds numbers. So Reynolds numbers smaller than 1. And here we have no lateral convection and adjacent lamellae do not interfere. So what does this second sentence mean? For this, please look at the right-hand side. You can see here a channel. And as you can see, we have some liquid in this channel. And please imagine that here you have a pressure, here you have a lower pressure, so our fluid starts to move. And we now imagine that the flow consists of individual lamellae, which are indicated here. So you have all this kind of lamellae, and these lamellae do not interfere with each other in Stokes flow. So there's no interaction between those different layers of flow. The second regime is the laminar regime. Here the Reynolds number is higher than 1, so we do not have Stokes flow anymore, but it's smaller than a critical Reynolds number. And the critical Reynolds number is not a universal number, it's dependent on your problem. So for pipe flow, we usually consider the critical Reynolds number to be in the range of 2,300. So if you have a pipe and your Reynolds number is lower than 2,300, your flow can be considered as laminar. And in a laminar flow, you still have these lamellae right here, but you now have lateral convection. So from time to time, you have some interaction between those different fluid sheets. And if your Reynolds number is higher than the critical Reynolds number, your flow becomes turbulent. Then it does not look like this anymore. We will see how turbulent flow looks like in a second. So these three regimes are illustrated in this video, which I'm going to play now. So you can see that here you have 4 different lamellae of flow. So illustrated is the velocity component. As you can see, those flow from left to right, and you don't have much interaction. And over time in this video, the Reynolds number is slightly increased. Here you already saw some instabilities. And if we increase the Reynolds number even further, you can see some kind of eddies forming. The flow starts to swirl. And now you can see that it becomes fully turbulent. So you don't have those individual sheets anymore. You have swirls and eddies inside this flow. All right, on this side, you can see a comparison of laminar flow and turbulent flow. In laminar flow, the liquid sheets with different velocities slide smoothly along each other. So this is illustrated right here. And this means that you have mixing only due to diffusion. And laminar flow is predictable. In turbulent flow, the lamellae disintegrate and form eddies, swirls, or vortices, as illustrated here. And turbulent flow is chaotic. And what does it mean? To illustrate this, please imagine that you measure the velocity at one specific point in the laminar flow and the turbulent flow. So you have one point where you measure the velocity, and this point does not change. And if you now record the velocity over some time, you can see that in the laminar flow, it remains constant. So the velocity on this point is always the same velocity. In turbulent flow, you also have some kind of mean velocity, but this mean velocity is superimposed by chaotic fluctuations.